energy for the weekend webinar by Gabrijel Energy and our partner Enerchange. My name is Alexander Richter. I'm the founder of Gabrijel Energy, and I'm very, very pleased to have with me today Gabrijel Grubac, a senior completion engineer with Mazama Energy. And he will be speaking about a rather interesting topic, and this is SuperHot rock geothermal, here in the context of the Newberry Volcano project, which was initially set up as an EGS project back then with Alterrock, and was actually in the running to become a Forge project, and is now being pushed as a SuperHot rock geothermal project. And of course, this is, no pun intended, a super hot topic. So very pleased to have Gabrijel with us today and sharing updates from the project. We will have, or you will have, the opportunity to ask questions in the panel here of the webinar. After the presentation, we will try to group presentations and we'll have see how much of those questions Gabrijel could then answer. And with that, Gabrijel, over to you. Thank you so much for joining us today and presenting on the project.
Good afternoon, Alex, and everyone else. Thank you for having me here today. It's a pleasure to be at the start of the year talking about a project that has been really a milestone in the super hard rock world in the recent months. And I'm looking forward to share insights about our projects, and hopefully will do my best to answer the questions of the audience. So, as Alex mentioned earlier, we are finding ourselves the Newberry Volcano in Oregon, talking about enhanced geothermal systems above 300C. And my goal today is really to walk you through how it all really began with one of the milestones that we've achieved in 2025 in terms of our pilot project, and what that really means, not just for Mazama, but essentially for the world of geothermal in the near future, and what kind of opportunities and possibilities will it open for clean energy production, and changing really the landscape of how energy is distributed in the world and from which sources. What you see on this picture is the beautiful site where it all started from the very beginnings, and I will walk you through the story. Before I get into the project details, I wanted to bring to your attention, and I'm sure a good part of the audience is already aware of it, on what really the super hard rock resources are, in the sense of how vast and accessible they are. You look at the whole world and look at the possibilities that are there. We obviously know areas of the world where the thermal gradient is quite high, you know, the ability to reach high temperatures at shallower depths, but that still remains a great thing for those areas, but a pretty localized ability to tap that energy. But now you look at what the super hard rock capabilities are, and you look at the 400 degrees C isotherm. Essentially, what you see in the orange are depths between 1 to 10 kilometers. And if you take into consideration the past in terms of drilling, not only in the geothermal world, but in the oil and gas as well, fairly easy to reach these depths. What becomes more difficult is, you know, the type of rock you're working with. And so I'll give you some insight on that later when we talk about the drilling of our wells. But what this really shows is a big potential in terms of terawatts. So the capacity, the potential is huge. If you look at what that would mean from a world power consumption today, I mean, the numbers are staggering. Now, coming from let's say, sober technical perspective, this is what the potential out there is, and there is a very strong way forward in being able to tap into these numbers, and being able to change really the energy landscape. So take a look at this map, understand that the opportunities are large, that what we've done at the Newberry Volcano really is becoming a super hard rock blueprint that we can use across the world and enable the production of such a dense energy source itself, right? And to give you a sense of comparison, you know, what you see here is a little bit on, if you were to look at a shale gas, you know, typical Haynesville well in the oil and gas world, and then you looked which is in the range of 150 C or below. Conventional geothermal, which is, in the range of 230 C. Looking at the depths and placements, and EGS itself, the binary EGS below 200 C, and then you come up to these temperatures, supercritical temperatures above 375 C, and now you see this big potential. Now, these are numbers. It gives you a scale understanding of what super hot rock could do and why is this big power density in there. You look at enthalpy itself as we get hotter in temperature and the ability to harness the temperature, the power cycle efficiencies, and ultimately what are the flow rates that we can enable in order to harness that heat. And you start crunching numbers, they become very, very realistic in how super hot rock, with the power density that it brings another big aspect to it, and it's the footprint. You're now minimizing footprint. So in order to have a setup that will bring this much megawatt electric on surface, drill less wells. And that is extremely important, because ideally what we're looking at in the future is we're looking at a decreased footprint, less wells, ability to harness more energy from these wells, and work, hand in hand, with the environmental aspect of things, and just showing how much more geothermal is in terms of not just being a dense energy source, but of the footprint that that it could take. So keep an eye on these numbers, because they mean a lot for the ability to produce electricity and what that would mean for the areas where this is being done. If you look at conventional geothermal, hot rock, ability to circulate water, there's permeable rock. So essentially that fluid has a path to move through. And there's been projects around the world that have done in that context a decent job at extracting the energy itself and being able to pump water downhole, harness the heat, bring it back to surface. But I want to take your attention to this other side of the slide, and essentially it's what an enhanced geothermal in hot dry rock would look like as the one that we have done. The ability to engineer a reservoir volume. This is what we're after, and this is what we've achieved in our pilot, is the ability to capture the subsurface heat, but in a way where we can design that reservoir itself and be able to inflict in it a flow capacity using propping materials that would keep these pathways open. And that's what I'm looking forward to show you shortly. So 331C, this is a number that has imprinted not only in the team's mind at Mazama, the work that we've done, but it's one that we were proudly sharing recently in 2025. And it really was the downhole temperatures that we were able to work with in order to enable this project. And it's a large number. And for those that don't work really in degrees C, this is in the range of 630 degrees F, big numbers. What was thought before not really possible, and if it was done possibly, it was done for a very short period. What we're going after is hot temperatures and looking at longevity. We want these systems to work for longer. We want them to bring energy to surface in a sustainable and meaningful way. So what you see on the left over here is our 2025 EGS pilot. I wanted to give you a brief summary of it. We were able to de-risk technology and achieve connectivity between the wells. So we had an injector well and a producer well. And why is this important? It's important to set in the ground of what the expectations were in terms of de-risking technology. Looking at these temperatures, there was a lot of thought process on how do we run downhole tools? How do we make sure that we're keeping the equipment cool? How are we creating the reservoir? And how are we enabling these pathways where we have increased flow capacity? And part of that was the utilization of our proprietary stimulation technique, thermal lattice code, where we've worked in the lab, done all the testing, all the validations with samples of the mineralogy that we were going to work with, and implemented that in the field with measured impact in terms of flow capacity itself. And so we saw that it works greatly in the lab and that it can work in the field, and it has brought a big advantage. We had 24/7 field operations. You're looking at average ROPs of 72 feet an hour. That's about 21 meter to 22 meters per hour. And I will get into more detail in this, but we were pleasantly not surprised because we were planning for these things, but it was a pleasant experience to go through the drilling process and understand that that is not really the bottleneck in enabling EGS. And what's really important is the injected fluid loss in EGS, one of the critical aspects in it. We're looking at, efficiencies where we want a loop, an open loop that is efficient and there's not much of a fluid loss. And last but not least is you look at these hot temperatures and the setup that we're in, we want integrity demonstrated. We want the ability to see that the casing can hold the temperatures, the cycles, that we're not losing integrity through the whole process. And we've managed that. And through months, we've managed to see, when I show you the timeline of the work that we've done, that is possible. And at the end, looking at what this really meant, as per Dr. McLennan's quote, but it was a fulfillment of a vision from nearly 50 years ago. So it all started, at the Los Alamos National Lab at Fenton Hill, but essentially we came full circle. We're able to do something that took a lot of planning, a lot of work. And as Alex mentioned earlier, there's been work at the Newberry in the past years of initial testings, trying to understand the reservoir. So a lot of courage into stepping into that, but ideally what we managed to do in the last couple of years is bring this to reality and what this could mean for the future. And so Mazama itself, if you look at different kind of systems, it is architected to unlock SuperHot rock EGS, and this statement is carried on by the actual field work that we have done. And so it is a pleasure to be part of the team and be part of this group that's pushing the boundaries, the ability to pump down water and harness the heat at these temperatures, the enthalpies that we're looking at. Do we see that future of tens and hundreds of megawatts bringing power? Well, we do, and that's an exciting update I want to give you at the end of this presentation. And so we've also, in the work that we've done is identifying what are the attractive areas for SuperHot rock EGS power generation across the U.S., looking at drilling depths. Newberry is 3.7 kilometers, and we're reaching those temperatures that we're looking for in terms of supercritical. If you go to other areas, there'll be a difference in depth. But the great news there is that we have a lot of the learnings from the drilling process. We've built plans on how to get to these depths, efficiency, work on the economics of the drilling itself. But ultimately, what should this do for us? Getting us to LCOEs that are competitive with the hydrocarbon world, that could significantly impact the way electricity is being produced in an economic matter. So not just an experiment itself, but one that actually changes the outlook on electricity production. And so SuperHot rock, what we've looked at, collaborating with hyperscalers to select these best locations, and really it comes down to being the ideal source for powering these mega data centers. And there's been a lot of interest in the industry from this perspective, and from the perspective of geothermal, more than happy to be part of that and be able to supply this kind of energy. What you see here is a beautiful picture. It was a site close to the site of where Mazama has had its AGS pilot and the demonstration project. A beautiful area, an area that carries with it a lot of history when it comes to the geothermal background. And to give you a little bit of an understanding, the Newberry site is large, is a diverse EGS lab resource. So we're building on 50 years of data. There's a lot of information that had initially been available, a lot of information that we have made available, and that we're actually pretty proud of, because we have learned so much from just physical tests done on the information itself, which I'll share with you shortly. But 2 deep geothermal wells were drilled in 2008, back in the day, essentially. And what we're looking at is, 50 square kilometers of federal geothermal leases on the western flank of the Newberry volcano. And so we have the area to work with this. But if you go in the subsurface, before going into the subsurface, just want to give you a sense to those that are not informed with the Newberry work. Is the area is close to Bend, Oregon, so that's where the site location it is. And once you get into the subsurface, this was the well 5529. Remember that number? That's the injector well that we have worked initially with. But essentially, where is this heat coming from? from the magma chamber, so the source of the heat itself, and what are the types of rocks that we're dealing with, right? And so if you look at the very right bottom here, we're working in this domain over here with basaltic rock, with granodiorite, and the experience of working with different lithologies and trying to stimulate them is a very, very meaningful one because of how these treatments behave real time, and all the learnings that we've captured through those. So 331 last year was achieved, but let me walk you through the how a little bit. This is a picture of the site in the winter. It's a beautiful picture. It looks probably very, very appealing from where you're at right now. I can tell that during the winter, if you're out there, it's an interesting experience. So a lot of the challenges that we had to work with, they were not just related to the subsurface, but also to the surface and to the weather. You know, being able to do work in a meter of snow, being able to move equipment and get everything put together to deliver this project. It was a big challenge, but one that we surmounted together as a team. And so, you know, you look at the challenges themselves and what are the rig capabilities, the ROPs that we can achieve in different kind of rock scores. We were not working with a single lithology. Temperature management, managing temperature for the sake of the tools that are being run downhole. A lot of the questions that a good chunk of the industry has is, can we run these tools downhole at 400 and above without them failing immediately and not working? Casing itself, the cement, so essentially the isolation between the casing and the reservoir itself, corrosion control, completion and stimulation. How do we complete these wells and how do we effectively stimulate them in a way that we can sustain longevity in terms of flow? This is one of the critical aspects of what Mazama works on, of what thermal lattice is about. The ability to not stay within the weeks or months of circulation, but projects that can last for years and produce electricity efficiently, right? And that really comes down to the longevity. So not just the longevity of the completion equipment downhole, but the longevity of the system that we have created through the fractures and the materials that are being used. So how do we engineer this 331C project? What you see over here is a layout of the site during the stimulation work. There was a lot of work that was put in place in terms of volumetrics, in terms of logistics, ensuring that all environmental aspects are being followed, taken care of. And so starting with 5529, which was the injector well, it was a challenging re-entry. So this was a legacy well, a well that already existed, but we had to do a workover in order to pull, let's say, the slotted liners that were installed back in the day, and just install a completion that we thought was the best solution in order to create that reservoir that we work with. So starting with that slightly deviated double casing, so through 4.5 inches, 7-inch slotted liner into types of rocks that were really an experience during the stimulation. A hybrid setup in terms of fluids and equipment, so thought process on how do we deploy these fluids downhole, what kind of fluids are going to be deployed downhole, how do we carry that propping material that will keep these fractures and pathways open, and what is the main approach of connecting to the reservoir. So once we got out there, we had plans in place with contingencies on how do we connect from the wellbore to the reservoir itself. And so our main approach was abrasive perforating, a technology that was known in the industry, especially in the oil and gas world, but that we had fine-tuned for the application on site. And then I'll walk you through the story of how we learned through fiber that we were able to cool efficiently and be able to run different kind of tools downhole. And so once the stimulated well, you know, the injector was stimulated, we had to plan for drilling the producer well, so essentially a well that would capture that fluid that's being injected and produce it to the surface. But this well had to be placed efficiently in such a way where it would drill into the stimulated reservoir area, the engineered reservoir. And how do we work with all that? So that was a whole process in place. And then once the well was drilled, the stimulation of the producer took place. And what we did is we had a design in place, but a lot of the learnings from the first phase. So it was really a real-time process of what can be done to enhance these connections. And at the end of the day, once the stimulation was completed and we saw confirmation of connectivity during the stimulation itself, which I will be biased, but myself and the team that was out there, that was a pretty great moment. Seeing for yourself a pressure change, a signature, that a proof through the fiber that you've connected the two wells, and then essentially after that circulating fluid, so pumping into the injector, flowing through the reservoir volume, and then bringing it up to surface. The other aspect of the operations, as you might be aware or not, is with EGS comes the responsibility of watching real-time seismic monitoring. And so what we had in place is, 3 independent networks. The Lawrence Berkeley network itself, and what you will see here in the map is what's marked with the 2M, these inverted triangles, and then the Pacific Northwest Seismic Network itself, and the USGS, and then we also had a permanent fiber data coming from the injector well. So what it took is, for our chief geoscientist and geoscience team to keep a close eye on these, keep a close communication with the national labs. We had an ISMP in place as expected in this kind of operations, a very intricate one that had a strong operational plan attached to it for making decisions real time, but essentially monitoring the induced seismicity, any kind of events and magnitudes. And we were always in the green. The number of events, the magnitudes were below zero, nothing out of the ordinary, safe operations, but with a very robust plan on how to do that. On the injector well, as I mentioned earlier, we've connected to the reservoir through the double casing, and in itself, you can see the challenge for those that are involved in the completion world, but variable lithologies themselves, basalt, andesite, granodiorite, so a change in mineralogy, and what that brings with it is complexity in terms of how do you generate fractures, but also what it brings with it is a wealth of information that we're very glad to have, because that helps us enhance the learnings and plan for the near future. Diagnostic technology, so we talked about the fiber, extremely important. We'd install a fiber that can see temperature changes, and what you see really here is we were able to get profiles of how much fluid is being pumped, how fast is the well cooling down, what is the heat back once the well's cooled down, how long do we wait, and that's where real-time work with other teams was quite amazing. Is we learned that not only can we do abrasive jetting, but we can now apply oil and gas technologies such as composite plugs for isolation or wireline conveyed perforating. It sounds easy when I say it. I can assure you it is not. It requires a lot of planning, but what we did manage to do is show and enable that approach could be done. And then, get into pumping mode and being able to stimulate. And what you see here is an example for those that are in the stimulation world. You will see that, there's moments where there's a little bit of tension, trying to understand how the formation is behaving, but all handled real time, 0 screen outs throughout the stimulation of the injector and the producer, and the application of the thermal lattice itself, trying to understand what the fluid leak off looked like for these stages, and then, understanding how to couple that with tensile failure and get the results that we wanted. Interestingly enough, we had done a flowback response test after the stimulation of the injector, and because we had used nanotracers in the fluid, we see a signature from every stage in that sample that was taken on surface. You might imagine that made definitely myself happy and the team, knowing that we had just from the stimulation of the injector itself a hydraulic communication between the stages. So injector well was stimulated. We now get to the segment where we have to drill the producer well. And our drilling team has done an outstanding job with the service providers working together. Please bear in mind, we're doing this through the winter months, through the snow, through the ice, through lines freezing, through making it work. For those that work in cold regions, you will understand what that means in terms of challenges. But really what that meant is they got us to bottom, to the depth. And when I say they got us, I mean the reservoir creation team, from all the planning on how do we connect these wells, and had some pretty impressive numbers. You look at, the ROPs, and 76 feet per hour was an average, rate of penetration versus 20 feet per hour for the offset well. And there were segments where the ROPs have reached even 100 foot per hour in hard crystalline rock. So those are peaks. And they're important to mention because they show us that we have the ability to increase this drilling efficiency. And that really is the plan in the near future in terms of enhancing times and getting us to bottom. And if you look at the thermal management of the tools, there were no thermal failures of BHAs or MWDs. And for those in the drilling world, that's a big thing. I don't come from the drilling world myself. I'm in the completion. But you can appreciate what that means is the ability to cool the tools and run them downhole. And you see this difference in temperatures. It's quite impressive. But how you manage that, how you run it, what's the timing, this is critical. And that's where the team's capabilities, really came to surface. Well, integrity itself is a big, concern in different kind of settings, but we were able to achieve that through the process itself. And one thing that really proud of the team is the ability to retrieve a core. So we managed to retrieve a core at over 300 degrees Celsius. And what you see it here, and these little arrows are there for a reason, and I'll show you shortly why. But we've taken this course and we've managed to gain so much insight in mechanical properties and the way these rocks behave in building what the future would look like. So we've drilled, we've placed it where we wanted to be. We'll now have to stimulate the producer. You know what these arrows are showing? Proppant. So the propping agents that we had pumped in the injector well, when we cored through the drilling process, the proppant particles were encountered. That's a significant proof of connectivity in itself. But the implications that it has in terms of, stimulation modeling and understanding proppant distribution, proppant transport, it's a science in itself. But being able to see it on surface, quite a success, I would say. We've optimized the stimulation design. We've run a hybrid fluid approach, so also pumped the first crosslink fluid application in the world. So the ability to pump a higher viscosity fluid downhole to carry the proppant itself. A lot of testing with the fluid, a lot of angles to look at the concerns that what that might bring in terms of, ability to carry the proppant into the fracture and hold it into place. A lot of modeling that came with it and the cool downs that would allow that. And then the forward thinking from the team in Mazama is how do we enable, different kind of connections from wellbores to reservoirs. And we had worked this for months, but we were able to run a sleeve in stage one, essentially being able to open and stimulate through it. And so that was quite an achievement. The thermal lattice application, as I mentioned earlier, from the injector, again, it's a learning process through time. And then what it came down, and if you're looking at the stages over here, really is the pressure response on the injector while we are stimulating the producer, and you start seeing these big jumps and pressures, and that's part of the work that we have done is trying to understand these slopes and changes and what kind of connectivity that means. But we had proppant in the core confirmed, we had pressure interference confirmed, and we had tracer testing. And so those nano tracers that we had used in the injector well and used the unique ones in the producer wells, we took flowback samples, and essentially what that meant is we had a signature from every single stage. Now, the connectivity in the reservoir and the morphology of the fractures, that's the work, that was done and is being done to try to understand as best as possible. But having the signature from all this tracer, it was just there, physical proof of meaningful connectivity between the wells and the ability to flow fluid through it. We had also run chemical tracers, some of it, testing some of the, pushing the limit essentially in technology from one well to the other, pumping into the injector and then, producing in the producer. And we've taken, the data that's been shared with us in terms of the time that it took to see these tracers on the other hand, the residence time, and then we're working with all this information as we had run, the first circulation, the circulation test. And what's interesting is at this time there's an ongoing reservoir calibration and testing. And what that really means is if you go back to my words at the beginning, it's a pilot de-risk project. And so what we're doing is maximizing on the learnings, because these learnings are built into segments, whether that's, geoscience and the subsurface data that we have, or it's drilling and trying to improve even further the ROPs and get our efficiencies higher, completion, what kind of tools are we going to run and fluids to pump place that prop and downhole, but place it in a meaningful way that will give us longevity through the system. And what all that means, when you tie when you come to the conclusion in itself and understand that 331 C on bottom, ability to connect the wells at a certain spacing between them, and what that implication of spacing means for the future when we do the future work. And so when that comes full circle, you'd ask your question, what is next? And next is super critical for the work that we're doing with the team. We are pushing the boundaries of really what's possible. Pretty great achievement last year. We are very aware of the technical challenges that come with it, and that's why it's a pleasure to be part of this team, is that the potential is huge. We have achieved something particular that changes really the whole SuperHot world, but we're also aware of the technical challenges, and what's great is that we're addressing each and every challenge with a solution coming from the team, whether in whichever discipline that's part of. And so what this really means is, if you look at our 2026 plans, and this is where I would say my talk will culminate, let's say, we've completed our EGS pilot in 2025 and taken all the learnings. And please keep an eye out in the next couple of months. The Mazama team will be sharing a lot of the technical work through technical publications of what we had done in terms of drilling and completion and the geoscience aspect of it. So keep an eye on that for more, granular information that we're able to share through the process in itself. But really what it comes down to now is 2026 and a full-scale commercial pilot. We are not talking about technology de-risking any longer. We are moving into a commercial realm. So the plan is to drill a horizontal well pair that will output 15 to 20 megawatt electric net power, and that will really, and keep a focus on this, be the foundation for a 200 megawatt project. What I'm talking about is not just a wish, it's in the process of planning, and it's the sum of all the work that has been done at Newberry in the last couple of years from all angles and all the learnings that we have done. And it's quite amazing, being here presenting to you this, because it's palpable, it's a real project, and this is the plan. Another big part of the plan itself is the testing, the running of supercritical CO2 drilling in ultra deep SuperHot wells. So that's part of 2026's plan. Mazama in itself we're going to be busy. We're looking forward to this. We're looking forward to turn testing into commercial, because ultimately that's what it needs to be, is the ability to harness the SuperHot rock potential, not just in Newberry, where we have learned and we will do it, but create a blueprint that can be applied in other places in the world, and bring this very dense energy source to surface efficiently. With that, I think I have completed my part, Alex.
Excellent, Gabriel. Wow. Of course, you fulfilled the expectations and more. I think this is also the feedback here from the questions that we have so far, and I don't expect that people will stop asking questions here. So please go ahead. No, but overall, I guess feedback very positive and very excited. So congratulations on this, of course, also from our end. And of course, it's going to be a bit difficult kind of going through these questions in a sense of trying to group them as much as possible. So I'm trying, might not be that successful, but I guess here's a technical question in a sense or technical or more business question is comparing, let's say, traditional drilling for traditional hydrothermal projects kind of and drilling in these, let's say, high temperature of fields, kind of how do you see the well costs in comparison? Is by what factor do you have to calculate in kind of what the higher drilling cost is?
That is a really good question, and just disclaimer: my drilling colleagues will do a much better job than me at this. And like I said earlier, it's important to keep an eye for the upcoming couple of months, where we'll be sharing the technical work. As part of that will include the answer to these kind of questions. But essentially, the economic model itself, it's segmented when it comes to the drilling process itself, in depths, right? So just looking at the initial depths that we're drilling into and the approach that's going to take, the string design in itself and how it's going to look like. And most critically, Alex, is the ROPs that we've achieved and the mechanical testing that we're doing on these core samples that we've had. So coupling all these learning, and so how are we going to approach this in terms of the PDC bits themselves and the type of technology that's going to be run down. So it's really holistic. I wouldn't be able to pinpoint an exact segment of it because each and every one plays a role, but our goal is to enhance these times 20 to 30%, and try to get these costs down. Now, I will make a comment, and I think it's important to keep this in mind. Drilling is not the leading cost for EGS. In itself, it carries a big chunk, and I believe the industry has always kind of carried that load. But what happens to emerge now is the completion side of things, and it's the ability to plan these engineered reservoirs in such a way that they can connect efficiently, but they carry a cost with them, and that cost is significant and close to what other costs might look like. So I think it's important for us as an audience is to keep that in mind, that it's when it comes to economics of EGS, it's not just drilling driven.
Okay, thanks. Okay, now the questions trickling in, so I'm trying to cut to the chase here. What's the distance between the injection and the production well in this case?
Good question. Straight answer. It's about 100 meters. And that number is not just a number, a round number that you might think. It's a number that was designed with months of work, and it carries implications, like I mentioned earlier, as how do we design the future horizontals? And the industry has done work on this, and in a way where we can harness the heat, avoid short circuiting, and really, Alex, it's about the longevity of the systems. How long can we harvest the heat efficiently? And so this is what this spacing has done for us, is we've worked around it. We were able to connect. It's what the learnings from it come.
Then the question here, how do you plan to overcome the 8% water losses?
So that's also a good question. In the world of EGS, ideally, you would want 100% efficiency, not to make up for any of the water. But here's the kicker. With SuperHot rock, because the footprint is lower, the need, and because of the enthalpies that we're working with, the need for water volumes is lower than what you would have in other cases at lower temperatures. And so starting from that, the requirement for water is less than what it really would be in EGS. Making up for it, ideally what we're working on is during the stimulation process itself, you have to work with the fluid loss. And I can tell you firsthand, I've had that experience. And so how do you walk that through the stimulation process? But at the end of the day, once you get into heat harvesting, there's a creation of dominant paths that with time will enhance this loss. And at one point, you can't go against Mother Nature. And so it's very important to stay technically sober in that sense. And that's the work that we're doing from the geoscience perspective, is trying to characterize the subsurface and what are the areas that we're going into. Because if you're going to drill into secondary systems that are leaking off, 70%, you now might be in challenging waters, pun intended.
Okay, well, this is going to be a lot of questions here now, so let's try to kind of maybe cut this short to the best way possible. Here's a question: what mass flow rate did you get?
That is a good question. Those answers will come in the very near future. So when it comes to the mass flow rates and the temperatures, that's going to be coming here in the near future. Like I said earlier, the reservoir equilibration mode and testing is ongoing, and that. Just stay tuned for this. What we're seeing is positive, very positive, and what will come in the near future, we'll be able to share with the world to the extent that we can, and then we're going to take again those learnings and put them into our horizontal planning as well.
How do you currently diagnose and quantify heat exchange efficiency along the wellbore and reservoir, and kind of with what methodologies, if any, are used to optimize it over time?
That's a great question. So Mazama has its own module, and if you look up the tools that we have, one of them is called Heat Harvester, led by our reservoir lead in the team. Essentially, we've created a tool that does all that work from surface through, so the wellbore dynamics itself, through the fractures, into the producers and back on surface. And so it's a full cycle modeling tool that we use for all the work that we're doing. I would not be able to get in detail into it. It's called Heat Harvester. There's been a presentation at GRC last year in Hawaii. So you can always reach out and I can send you the reference technical papers that you can read on how the tool works and the actual thermodynamics behind it.
Okay, we will definitely not be able to answer all the questions here, but let's try here going forward. What was the surface temperature at the wellhead and tree, particularly for the producer well while it's producing? And have you seen any issues with the wellhead system required for these types as well operating at these high temperatures?
We have not seen issues. So the process planning has been pretty efficient from the team. But like I said earlier, so when it comes to temperature profiles and sharing, that will come in the near future.
How did you obtain the location and geometry for the of the magma chamber? I mean, I guess that's supposed to the question. Has there been any data that you got from the Alta project, from the initial one, to kind of to work with?
Yeah. So a lot of the subsurface information, and like you mentioned earlier, Alta has done some of the work in the past. And as I mentioned in my slide, this is years of data collection. So our geoscience team has really captured all that. And based on that kind of information, built on what should we be expecting downhole, and then coupled it with the real, sampling, the coring that we have done. And so what we're doing now is we're recalibrating, understanding this. And one very important aspect to this is we will be drilling into SuperHot soon in 2026. And so what we plan to do is to utilize that information to keep calibrating these models.
Here's a good question. I guess that's also kind of like it's a general EGS question here. Once heat exchange inefficiency are identified, such as short circuiting or uneven thermal drawdown, what mechanisms are available today to optimize performance, and how is that measured?
That's a great question, and I would say that's one of the biggest focuses, not just in Mazama but generally in industry. The path of least resistance is something that we can't run away from. Fractures will do what fractures do, but one of the ways that we are counteracting that is the fracture design works. We have a specialized way of planning these horizontal wells that are coming up. The conductivities itself that we are creating, and so the work that's being put in that is extremely important. And conductivity is really, for those that don't work in the stimulation world, essentially is the ability to flow through those fractures, and the distribution of this conductivity would also drive the distribution of the flow along the laterals. So we're doing some really high temperature testing on proppants, and Mazama is actually quite excited about this, Alex, because we'll be using real world data to calibrate the models, and then also looking at solutions in terms of well completions, away from just a plug and perf perspective, but ability to use, mechanisms, sleeves and orifice flows and maybe inflow devices. And so this is all being under the process of studying, let's say, and ensuring that we can plan for it to mitigate, short circuiting and to ensure the distribution in the laterals as uniform as possible to capture the heat.
Here, you might have touched upon that, but question is on how did the surface equipment well and valves withstand the combination of pressure and high temperature?
Well, the short answer is they did. We ran into no problems in doing that with the approach that we had on the field. At this very moment, I can't think of the exact process that the guys had on the field of handling this, but I do recall that really wasn't a challenge, with proper planning.
Okay. What problems did lithology give you? I presume like mechanical ones, like casing.
Yes.
Mentioned here.
Beautiful question. I can speak from a stimulation and completion standpoint. Running into different lithologies and trying to, create these this engineered rock volume, it becomes challenging because every type of rock will behave differently. And I can tell you that we've had stages in basalt itself. We had stages in granodiorite itself. We had some combination with andesite as well. And the challenges that come with it is, using the mechanical properties and trying to understand the initiation of these fractures and sustaining the growth of these fractures and the combination with the leak-off parameters. Because what we did for every stage is run diagnostic testing to try to understand what that layer would behave in terms of leak-off. So every lithology carried an aspect from a stimulation perspective. It was very important. You can see that in the treating pressures, and we shared some of that work recently in some technical publication. But from a stabilization perspective, it carries that. From a drilling perspective, obviously, you will have areas where the ROPs are enhanced and areas where they're not, and so that's what the team is doing, is surgically trying to get the strategies done. What do you do when you're in granodiorite? What do you do when you're in basalt? I can tell you from personal experience, I'm not really a great friend of basalt when it comes to stimulation. That's what I can share with you, Alex.
Here's a good question. I mean, there's a lot of like really specific technical questions. Let me try to kind of get maybe to some of the general questions first. But what was the most important mistake or incorrect assumption made and learned so far in this project for EGS or for SuperHot rock?
I can tell you, so I'm speaking from a personal perspective. It was the thermal management, or the expectation of going to these kind of systems with such hot temperatures. Obviously, we had done the modeling work, but modeling will work until you do it in real life, and then you understand that some assumptions were maybe wrong. And I think I would say that, but in a very positive way, because what we had seen out there on the fiber was something that gave us a lot of confidence during the process. And so what we learned is the ability to cool. The times of cooling were a lot more aggressive than expected from a stimulation perspective. And so we use that in the process itself, in the wellbore, like I told you earlier, from abrasive jetting to wireline conveyed perforating, but also we use that in the modeling work that we did in cooling the rock in itself before we ran, stimulation fluids that would degrade at high temperatures. So that was a big learning, a very positive one.
How did you ensure cement and casing integrity during injection at temperature range of 310 degrees C here?
Yeah, good question. So from the cementing side, just to give you a little bit of background, all the strings were cemented to surface. We had applied foam cement, some light cement slurries, and in the whole process, when we would run that, we've had, integrity testing of the system itself. So that in itself is a big, indicator. And then running, temperature logs and trying to understand if there is any change in temperature distribution along these wells. So that played a big role in terms of integrity understanding. So coupling these with the work that we've done during the stimulation, we've done so many cycles. I think this is a critical aspect, is the cooling and heating of the system is really extreme. And a lot of the systems in the past have failed because of this. But because of Mazama's, way of approaching the reliability-based design for the casing and, pre-stressing of the casing and the whole process itself really, really set the stage for the stimulation work. So it all came down to that. It came down to integrity tests, temperature logs, giving us confirmation that we didn't have any breach. And then in the near future, we might be looking at different things because, again, I'm always going back to the longevity concept, right? I think EGS is a great, and we've seen some proofs in the world of it, but what we've created here, we want it to last in the future, what we're going to create in 2026. And in order to do that, we have to keep running tests, trying to understand. So say, our stimulation of the injector was in January 2025. Producer was later in the year. And so months passed by, and then we had a fiber that still survived. We had a well that had full integrity. These are the kind of things that, made us feel confident about the approach that we had and that it works. But how do we learn more from that? And that's still in the pipeline with the team.
How corrosive was the producing circulating fluid? Was it consistent what you anticipated, or would this change, would the water chemistry change the surface downhole material selection significantly?
Yeah, I would. So I would defer that question, like I said, here in the near future when we start sharing that. I can just tell you that geochemistry in itself, and you're aware of it, is critical, not just from a standpoint of that, but a standpoint of the interactions downhole through the fractures themselves. So we're keeping a big focus, and I think I'll defer this answer for the near future, Alex.
Oh, good. Did you use insulated drill pipe in the campaign? And if so, could you share experience with performance, particularly in terms of thermal insulation?
Yes, we have used insulated drill pipe. That's a hard yes. And in terms of the performance, keep an eye out because in a month, some of this work will be published at the Stanford Geothermal Workshop. So as soon as it is out, you should be able to, download the work, access it, and get through the details. But yes, answer is yes, we have run it, and we're working on how to optimize that even further.
Regarding cooling of the equipment, kind of how were some of the completion equipment and run tools cooled before they were set up?
So at the beginning, when we started with the braces jetting, you run in the hole, the temperature that you expected with, the temperature you're working with on surface. Winter had its advantages. The fluid was pretty cold, and so we knew we could cool the tools and run in the hole, right? And we've done the modeling that would enable. We looked at all the parts of the system that we're running. Can it do it? Yes, it can, and we did it. But the way we did it after that is exactly what I showed earlier in the slide. Is we had profiles of cooling and heating based on the barrel per minute and volume change. And so we use that directly then in timing on how we run the tool. So just to give you an example, we would run, let's say, a composite plug that was rated to 350 F, right? But now you're in a well that's 630 F water mole temperature, and you're enabling yourself to run it. And so the reason we were able to do this is because our cool down profiles were quite aggressive and the timings. And so this took like an operational good planning, right? Running in hole, being able to do the work that you're planning to do and coming out of hole in time. So it's also a little bit of a chase with time. And it worked. So fiber in itself brought a lot of huge value, not just from a temperature perspective, but also from the microseismics itself.
Let's combine these two questions. Number one, let's say if you were to assume like a potential power generation capacity from the wells that you've drilled so far, kind of what would that be, and kind of how was the project funded?
So the assumptions on the potential, we've done the work on that. It's in the single megawatt range, right? And that's just what's expected in terms of kind of these systems. Because what you have to remember, these are vertical, slightly deviated wells, and for those that are in the stimulation world, connecting these kind of wells is a real challenge. And what we expect and what we see is somewhat in line, right? And that's where I'll leave it for now. Before the other results are shared in terms of the funding in itself. If you look at Mazama's website, you will see that support initially came from Coastal Ventures in itself, and now it's kind of expanded. So for all of those that are interested, you can look up Mazama Energy's website and get some more information on that.
Excellent. I'm going through additional ones. in the SHR development program, is one-to-one injector producer anticipated, or will multiple producers be supported by a single injector?
Great question. So our plan for 2026 is a horizontal doublet, so it's an injector producer. And as we're doing that, I'm planning for the 200 megawatt development that will change in terms of possible triplet setup. So 2026 doublet, moving forward, it will change because ideally this is the plan, is the 200 megawatt commercial.
Got it. Here, I guess a geographic question in the sense of the current drilling site versus the planned 2026 program. How is it from the location to the initial wells of 2008?
So because our project is kind of in two segments, we will be using the existing space for one of those tests that we have in supercritical. And then for the horizontal wells, it will be a different setting because what we're accounting for is the subsurface, right? And in order to reach the temperatures that we want and the placement of the wells that we want, obviously you have to work with the surface. And that's kind of in the works with the whole team.
Here is a good question. What is the main decision or technology choice you need to make now for SuperHot rock to move from pilots to commercial deployment?
Oh, that's a 1 hour discussion. But I can tell you that, and I hope you received as well, is the technical rigor that we have is important. And that's the one differentiator within Mazama is we know what the potential is, but we know what the challenges are. Right now, we have tackled most of these challenges. And what we've done is we're finding solutions to the problems and challenges that we see in the subsurface, because you cannot do a project like this and claim that everything just went perfect. Things went well because we had planned for it, and then things that, didn't go so great in the sense of, okay, we learned that cooling profiles are a lot more aggressive, then we're using that to do better. So to answer your question, we have what to work with. And that's where the confidence, let's say, comes, and that's where all the planning for 2020, because if you think of it, this is 2026, it's January 16th. So I'm really hoping that in 12 months from now, we can have another catch up, Alex, and share with you that we have drilled these wells. So we believe that we have, because of thermal lattice, because of supercritical CO2, because of the way we're handling integrity of the wells, the whole package that Mazama has, the Muse package, is enabling us to do this. Now, there's segments that require improvement and optimization, and that's what we talked about earlier. Fluid distribution in the laterals, how do we complete these wells more efficiently? That's the kind of work that, is being fine-tuned right now.
Okay, we are running out of time here of technical questions. So let me just kind of pick a few things out of a multiple question kind of comment here. How many fracture stages were pumped in the injector and the producer, and was the producer well used to monitor the fracture deployment from the injector?
A total of 12, and really it depends on how you number these treatments. But the producer was not used to monitor the injector. What we did is during the injector, we had the fiber itself, the microseismic arrays available, the tracing diagnostics, and that enabled the injector stimulation. When we got into the producer realm, we had the fiber in the injector that we use, for cross-well strain understanding. So that was one. The tracer diagnostics, that was two. The microseismic arrays that I mentioned earlier, that was three. So when we were doing the drilling and stimulation of the producer, that's what we relied on. And then as we were making the connections during the job, we were trying to understand how meaningful these connections were and what caused this efficiency, right? So that's, or, if some stages are not as well connected, what would cause the inefficiency? But that's the approach that we had.
Excellent. And I think with that, we need to put a stop to it. Unfortunately, I think we only have like two questions, I think, left here, and maybe some details that we didn't cover. But I think in overall, we've been able to get too many of those questions asked. Gabrijel, thank you so much for the update, and let's pencil in that 2027 update early in the next year. And looking forward to hear then more from your company's updates through the papers presented at the various conferences. Gabrijel, thank you so much. Thanks to everyone for joining, and yeah, have a good weekend indeed.